Our first topic in unsupervised machine learning here is standard deviation. I doubt most data scientists would consider this topic to be a formal or conventional unsupervised machine learning approach. But for our purposes, I do think it fits nicely because standard deviation gives us a measure of what's normal, and then what is not normal is anomalous. And so that for that reason, it works well. And also the way you get the standard deviation is a simple calculation. So it's unsupervised. So by doing this for a individual number, you're able to establish what's normal and what is not. So that's why I think it fits nicely. Let's use a quick example. Let's just say that we have a server and we know that people use it on Saturdays, and we get 7 weeks of numbers for how many times it's been accessed. First week, it's this number, whatever that would be. This is just hypothetical. The next week, it's this number. The following week, and so on until week 7, we have this number here. Well, what we want to do is get my definition of standard deviation for our purposes. It's wrong, but I think it'll work, as standard deviation is really quite a bit more complicated as a statistical calculation. What I'm going to say is it's the average distance from the average. So when we take all these numbers and we add them up together, and then we divide by the number of values that we have, we get the average or the mean. And so then what we do is we find out what is the average distance away from the mean that these numbers are. Well, that average distance becomes, in our example, the standard deviation. Now, everything that's outside of this is considered to be not normal. Everything that's within it is considered normal. So when we look in our example, we say, well, what happened in week 6? Why is this unusual number above the standard deviation? And then in week 7, what happened? Why is it below the normal? D2 pokes its head up here. So we don't know. But the bottom line is these would be considered things to look into because of the way we established our normal range of data. Again, this is for a single number. What will follow involves 2 numbers, as it will make sense when we get to that. Our second topic is correlation or regression. Note that this involves 2 numbers instead of 1, as we had with standard deviation. What we have here is what's called a scatter plot, which is merely the intersection of 2 different numbers. For our purposes, we'll use a quick example. Let's say that here on our Y or vertical axis, we have the average number of engineers working on a given day. Then here on our X or horizontal axis, we have the number of times that these engineers access a particular server. You'll notice an obvious relationship here, that the more the engineers that are working, the higher the number of accesses to the server. And there's a very clear linear relationship here, that the more you have working, this line sort of follows the center of these data points. This is called the regression line. You'll notice, though, that some of these things are sort of outside the norm, if you will. This is where we get into anomaly detection. Why do we have only 2 accesses when 5 people are on? Maybe it's a Sunday and they're not doing a whole lot with the server. Maybe the server's down. We don't know. What's going on with us here? We don't know. But these are anomalies. I would also like to note that this this red line is a way that we can leverage this regression line for predictive purposes. So if we were to say, you can't have 2.5 employees, this is an average here, but let's say we had 3 people working, 3 engineers, we would expect to have between 5 and 6 accesses to the server. So you could say that if you had anything outside of this number, that it would be anomalous and maybe worth looking at, maybe alert your security team. But this is sort of the purpose of regression and correlation, and it is very commonly used, and it's very easy to understand, which is why I love it so much. Our third topic is k-means clustering. I'm actually going to cover this in a more of a generic style, and I think you'll see why in a bit here in a few slides. K-means clustering is basically asking the algorithm to go into the data and find k clusters. I'm not going to discuss what k-means means. It's just beyond the scope of this presentation. But you say to the algorithm, please go out and find me X number of clusters. So here we have a grouping of 5 just randomly created data points, which would typically be found in a scatter plot, like we saw with regression. But for the purposes for us is, if you say k equals 2, you tell the algorithm to go please find me 2 clusters. So it will do that, as we've done here. You may find that you want 3. So it will then go and it will find 3 clusters for you. So, however, is this unsupervised? Well, in a sense, it's not, because you have to choose k. And very often you have to choose this number and test it, iterate over it. You may say, typically, this is going to involve not just 5 data points, but potentially hundreds or thousands. And you say, give me 100 clusters. You may find that's too many. It's too busy. You say, all right, instead give me 50. So you're working with the same data, but you're iterating through. 50 is too much. So you go to 20 and say, that's about right. So you kind of have to work through it, but the beauty of it is that it will give you those clusters and help you group data. One thing you might notice again is that as you find these clusters, you may find data points that are outside of all the clusters. That would be considered anomalous. Anything that's outside of the norm. So that's kind of how this is used. It's also used for predictive purposes, so that if you get a data point that is just like regression, if you have a data point that happens to fall in the same values as you find here, then it would be considered to be the same type of data that's within that cluster. I'd like to take a minute here to just step away from k-means clustering and just look at clustering more generically. Here we're looking at a scatter plot very similarly in the way that we did with k-means clustering, but I wanted to sort of have a closer look at what this really means. Here I've got a scatter plot with height and weight, and you see you have these people here, individuals whose height and weight are the intersection point. That's what these data points are for. And you'll notice what is an obvious sort of a cluster going on here. Well, what's the point of this? Really, why are we looking at clusters? The point is to try to derive insights, to make some decisions, to establish some sort of assessment of what's going on. So why is it that we have this one group of people here that appear to be smaller? They're shorter and weigh less. Well, maybe this is an elementary school, and these are elementary school kids, and these are high school. Maybe these are female, and these are male. We don't know, but this is the purpose of clustering, is to kind of help you look at the data and make those decisions. The other nice thing about what you see here is that you can use this in a forward-looking fashion, so that if you get somebody, you don't know if they're, for example, elementary school kid. This isn't the best example, but if you know that they happen to fall in this area, their height and weight, then you can then assume that they are like the other people in this cluster, and that is to say it would be an elementary school kid. Whereas up here, if the person's height and weight fell in this area, you would say, well, they are high school. Or if it's male, female, the same thing. If the person's height and weight fell in here, you might assume that they are female. But there are, of course, men who are this size, and there are women who are up here. So who knows? The other thing you can do with this is anomaly detection. When you have lots of groups of data, but you have one that's sort of sitting out in the middle of nowhere, that's anomalous and would be worth looking at. And again, that can be looked at forward-looking. Anytime you have a data point that you later would find in this area here or wherever that's outside of the norm, that would be something you would look at because you know it's outside the norm. So that's basically sort of the point of clustering, and I wanted to make sure we had a look at that. Now, this could be any two numbers. We could adopt over the same example we used in regression and correlation, where we had the average number of employees here working, or engineers working on a particular day, and the access to the server. Instead of having that straight line, that regression line we saw, we might see this type of a pattern instead. We don't know. But this can be any two numbers here, and that's the point. And any area in compliance where you have this need, this can be used in this way.